In 2004, a megathrust earthquake struck beneath the Indian Ocean. It measured 9.1 and triggered a tsunami that killed over 230,000 people.
Scientists are raising alarm as the Sunda Megathrust begins showing the same hidden stress signals that appeared before previous record-breaking quakes. Unusual tremors, rising strain, and rapid tectonic shifts suggest something powerful may be building deep below the trench. Could these signs be the first warnings of a new megaquake? And what happens if the pressure finally snaps? Let's find out. Stretching thousands of kilometers across the floor of the Indian Ocean, the Indo-Australian plate moves steadily northeastward, pushing beneath the vast Southeast Asian landmass. This slow-motion collision has been unfolding for millions of years, shaping islands, raising mountains, and creating one of the most active seismic regions on the planet. At the boundary between these moving slabs lies the Sunda Megathrust, a massive fault line where two pieces of the Earth's crust grind, lock, and occasionally rupture. This subduction zone begins near the Andaman Sea and runs down past Sumatra, Java, and into the lesser Sunda Islands. Though hidden beneath deep water, its influence is visible everywhere. Indonesia's towering volcanoes, its rugged coastlines, and even its fertile soils all trace their origins back to this immense geological engine. It is a system defined by immense pressure, where the Indo-Australian plate dives beneath the Eurasian plate at a rate of roughly 6 to 7 centimeters per year. That may seem slow, but on geological timescales, it is relentless. As the descending plate is forced deeper, friction prevents it from sliding smoothly. Instead, it becomes stuck, locking portions of the megathrust in place. The upper plate bends and warps, storing strain like a stretched spring. Over decades or centuries, this strain builds silently. The seafloor may deform by meters, but its movements are too gradual for human senses to detect. Only instruments, GPS receivers, seismometers, ocean bottom sensors capture the subtle changes. When enough strain accumulates, the locked segment can no longer hold. It snaps back into place, releasing energy in a sudden, violent shift. This is what creates great megathrust earthquakes, events capable of lifting or dropping the seafloor and displacing massive volumes of water. The process is the same one responsible for historic quakes in Alaska, Chile, Japan, and New Zealand. But along the Sunda Megathrust, its effects are particularly far-reaching because of the densely populated coastlines that line its path. Understanding this tectonic setting is crucial. It explains not only why large earthquakes occur here, but also why they cannot be precisely predicted. The system operates on natural cycles of stress and release, controlled by forces far beneath human reach. What scientists can do, and continue to refine, is measure, model, and monitor these processes to understand how the fault behaves and what it may do in the future. Across Indonesia and the broader scientific community, researchers agree on one central point. The Sunda Megathrust is a powerful geological system, but there is no technology capable of predicting when the next major rupture will occur. Every statement from credible institutions emphasizes this. Instead of forecasting exact events, scientists focus on monitoring long-term behavior, measuring subtle changes, and understanding the fault's structural evolution. Agencies such as the Indonesian Meteorology, Climatology, and Geophysics Agency, BMKG, regularly release updates clarifying that while some segments of the megathrust show signs of accumulated strain, none display indicators of an imminent large earthquake. BMKG stresses that earthquakes arise from processes deep beneath the Earth, processes that cannot be timed or triggered externally. Their messaging is consistent. Indonesia is a seismically active nation, and preparedness is essential, but speculation can mislead and cause unnecessary fear. Research institutions echo this caution. The Earth Observatory of Singapore, which has conducted extensive GPS, offshore, and seismic studies in Sumatra and the Andaman region, notes that several sections of the megathrust have been locked for decades. This means they are storing energy, but this condition can persist for years or even centuries. A locked fault segment does not imply an imminent rupture. It simply reflects the natural cycle of plate movement. Similarly, studies published through USGS, AGU, American Geophysical Union, and major universities describe the Sunda Megathrust as one of the world's most studied subduction zones. Their analyses highlight regions of higher strain accumulation, patterns of slow slip, and interactions between neighboring segments. But each paper reinforces the same message. Strain builds gradually and silently, with no short-term signals that pinpoint when failure will occur. Scientists also emphasize that aftershocks, swarms, or isolated tremors common along the arc do not automatically lead to larger events. They are part of the megathrust's background activity, not predictors. Even changes in heat flow or deep tremor rates, sometimes referenced in viral posts, are normal features of subduction zones. When scientists speak publicly about the Sunda Megathrust, their tone remains measured. They acknowledge the potential for large earthquakes because of the fault's history, but they avoid dramatic claims or countdown-style warnings. Instead, they focus on clear, actionable advice, stay informed, understand evacuation procedures, and rely on verified agencies for updates. In short, what scientists have actually said is both calming and empowering. The Sunda Megathrust is a natural system we cannot control or predict, but with monitoring and preparedness, societies can coexist with the forces that shape their region. Stretching more than 5,000 kilometers from Myanmar to the deep waters south of Java, the Sunda Megathrust is one of Earth's most imposing geological boundaries. It is here that the Indo-Australian plate steadily dives beneath the Eurasian plate, sinking into the mantle at a rate of around 6 to 7 centimeters each year. This slow, relentless movement is the engine behind many of Southeast Asia's strongest earthquakes. Unlike a simple crack in the ground, the Sunda Megathrust is a layered system. At the surface, the region appears calm, lush forests, quiet villages, and long coastlines running along the Indian Ocean. But beneath this calm exterior lies a contact zone where two continental-sized slabs of rock grind, jam, and deform. This locked interface is where stress silently accumulates. The megathrust behaves differently along its length. In the northern section, near the Andaman and Nicobar Islands, the fault has produced some of the most powerful earthquakes ever recorded, including the devastating magnitude 9.1 event of 2004. Farther south, along Sumatra, segments rupture more frequently, producing a series of major earthquakes in the 19th, 20th L, and early 21st centuries. Yet other regions, especially the deeper parts of Java, remain comparatively quiet, not because they are safe, but because their cycles of movement operate over longer timescales. Scientists divide the megathrust into distinct segments, each with its own behavior. Some are fully locked, gripping tightly and building pressure. Others are partially creeping, releasing tiny amounts of movement steadily over time. And in certain places, deeper slow-slip events occur, movements that take days or weeks instead of seconds, invisible to humans, but detectable through precise satellite measurements. Where the plates meet, temperature and pressure change with depth. The shallow, cooler portion of the fault is brittle, meaning it can snap violently during an earthquake. Deeper down, heat softens the rock, allowing it to deform more slowly. This difference in behavior is why some earthquakes rupture upwards while others remain confined at depth. The megathrust also influences the region's topography. The rise of the Barisan Mountains in Sumatra, the deep trenches offshore, and the volcanic arc stretching across Indonesia are all surface expressions of this powerful collision zone. Every island, valley, and coastal plain in the region carries the imprint of the subduction process. Understanding this structure helps scientists interpret the long-term patterns of the megathrust. It explains why some segments have erupted in the past, why others remain locked, and why stress continues to shift along the arc. But even with this knowledge, the system remains unpredictable in the short term, a reminder that while we can study the Earth's machinery, we cannot yet control its timing. What recent research has revealed about the Sunda Megathrust? In the last 2 decades, the Sunda Megathrust has become one of the world's most closely examined subduction zones. Advances in satellite technology, ocean bottom seismology, and GPS monitoring have given scientists a clearer picture of how this enormous fault system behaves beneath the surface. These tools do not predict earthquakes, but they reveal patterns that help explain the slow, deep processes shaping the region. One of the most significant insights comes from dense GPS networks placed across Sumatra and parts of the Andaman region. These stations measure subtle ground movement, sometimes only a few millimeters a year. By comparing these motions over time, scientists can identify which sections of the megathrust are locked and which are slipping quietly. Recent findings show that certain stretches offshore Sumatra remain strongly locked, storing energy that has accumulated for decades. But this locked state is a normal part of the seismic cycle, not an indicator of imminent rupture. Marine research has added even more detail. In several expeditions, scientists deployed ocean-bottom seismometers along the trench to record small earthquakes happening far beneath the sea. These deep tremors reveal how the slab sinks into the mantle and how fluids circulate through the fault zone. The presence of fluids can weaken rock, influence the way stress transfers, and shape how the fault breaks over long periods. These studies help researchers understand why some earthquakes propagate upward to the seafloor, while others remain confined deep below. Another important development is the growing understanding of slow slip events, movements along the fault that unfold gradually rather than violently. These events have been detected offshore western Sumatra, lasting days or even weeks. To the public, they are invisible. To scientists, they are clues to the megathrust's internal rhythm. Slow slip events can redistribute stress, either relieving small amounts of pressure or shifting strain to neighboring segments. But again, they do not serve as short-term warning signs. Recent studies also examine how sediments and geological structures along the seafloor shape the fault's behavior. The thick sediment pile offshore Sumatra, for example, acts as a cushion that influences rupture speed during earthquakes. In contrast, regions with thinner sediments may allow ruptures to travel faster, contributing to more energetic shaking or tsunamis. Despite the growing body of research, every major institution, from BMKG to USGS, emphasizes the same conclusion. None of these observations provide precise forecasts. They offer understanding, not prediction. Scientists are building a clearer map of how the megathrust breathes, shifts, and stores energy across centuries, but the exact moment of any future rupture remains beyond reach. What these discoveries truly offer is context. They show that the Sunda Megathrust is active because the Earth itself is active, moving slowly, steadily, and without regard for human timelines. And by studying its patterns, researchers strengthen the region's ability to prepare, respond, and adapt to whatever the future brings. Today, scientists track the Sunda Megathrust with a combination of instruments that provide an unprecedented window into the hidden mechanics of this immense fault. From satellites orbiting overhead to sensors placed on the seafloor, every movement, however small, is measured and recorded. The goal is not to predict the next earthquake, it is to understand the system, observe its behavior, and provide accurate information for those who live nearby. Seismometers, both on land and on the ocean floor, detect tremors too faint for humans to feel. These microquakes reveal which segments of the fault are locked and which are slipping gradually. Over time, patterns emerge. Areas that remain locked for decades or centuries are storing energy, while creeping zones release strain more slowly. Scientists study these patterns carefully, translating subtle movements into maps that describe the megathrust's long-term behavior. Complementing seismic measurements, GPS networks track the gradual deformation of the Earth's surface. In some regions, the ground moves only a few millimeters each year, a motion imperceptible to residents but critical to understanding stress accumulation along the fault. Satellite radar adds another layer, measuring tiny vertical and horizontal shifts over hundreds of kilometers. Together, these tools provide a continuous picture of how the plates interact beneath the ocean. Ocean bottom pressure sensors contribute vital data for tsunami monitoring. When the seafloor is suddenly displaced, these instruments detect the change in water pressure and send alerts to government agencies. Systems like Indonesia's imminent do not forecast earthquakes, but they can issue real-time warnings when a rupture occurs, giving coastal communities crucial minutes to evacuate. Scientists emphasize the limits of current monitoring. Despite the precision of these instruments, no combination of sensors can reliably predict the exact timing of a megathrust earthquake. What the data can show are long-term trends, areas of high strain, and the fault's evolving behavior. This knowledge informs building codes, urban planning, and emergency preparation, turning raw geological measurements into actionable insight. Regular bulletins from BMKG, research institutions, and universities summarize observations and clarify misunderstandings. These reports stress that while some portions of the megathrust are storing energy, there are no immediate warning signs of a major event. The emphasis is on context and preparedness, not alarm. By observing the Sunda Megathrust continuously, scientists can translate the silent, immense forces of the Earth into knowledge that communities can use. The system is patient, moving over decades and centuries, but through careful monitoring, humans can coexist safely alongside one of the planet's most powerful and dynamic natural phenomena. Along the coasts of Sumatra, Java, and the surrounding islands, millions of people live within reach of the Sunda Megathrust. Scientists do not predict the next earthquake, but they can anticipate its potential impacts using computer models, hazard maps, and historical data. These tools translate the unseen movement of the plates into a tangible understanding of risk. Tsunami modeling begins with the seafloor. By mapping the depth, slope, and sediment composition along the trench, researchers can estimate how water would be displaced during a rupture. High-resolution digital elevation models of coastal areas allow these simulations to project the flow of water inland, identifying communities, roads, and infrastructure that could be affected. These scenarios are based on past events, such as the 2004 Indian Ocean earthquake, and incorporate variations in magnitude, rupture length, and local bathymetry. Earthquake modeling works in parallel. Using data from seismometers and geological surveys, scientists estimate how energy might radiate through the crust during a large rupture. They calculate ground-shaking intensity, the likelihood of landslides in mountainous regions, and structural vulnerabilities in urban areas. These models are not exact predictions. They outline a range of possibilities, helping authorities plan for both moderate and extreme outcomes. The results of these studies are translated into coastal hazard maps. Zones of high, medium, and lower risk are identified, guiding land use planning, building codes, and evacuation strategies. Maps show which areas are most vulnerable to tsunami inundation, which slopes are prone to earthquake-triggered landslides, and which critical infrastructure may need reinforcement. They are living documents, updated as new monitoring data becomes available. Communities benefit directly from this work. Urban planners, emergency services, and local governments use the models to design evacuation routes, build vertical shelters, and plan drills. Coastal towns along Sumatra, Java, and the surrounding islands practice these simulations, moving thousands of residents to higher ground in exercises based on the projected scenarios. In this way, the work of scientists translates into real-world preparedness. Ultimately, these models and maps do not reduce the immense natural forces of the Sunda Megathrust. They cannot slow tectonic motion or prevent ruptures, but they do offer insight into what might happen and where, giving societies the knowledge and tools to respond effectively. By combining detailed scientific observation with careful planning, researchers transform abstract geological processes into actionable strategies that protect lives and communities. Living along the Sunda Megathrust means coexisting with a system that can release enormous energy without warning. Recognizing this, Indonesian authorities have developed comprehensive preparedness measures to reduce risk, combining scientific monitoring, emergency planning, and community engagement. One of the most important tools is the Indonesia Tsunami Early Warning System, INATEBS. This network links ocean bottom pressure sensors, tide gauges, and seismometers to detect sudden vertical shifts in the seafloor. When a significant displacement occurs, alerts are sent to government agencies and local communities. While INATEBS cannot predict earthquakes in advance, it provides critical minutes for evacuation once a rupture happens, valuable time that can save countless lives. Preparedness extends beyond technology. The government conducts regular simulation exercises, often in collaboration with international agencies and local organizations. Coastal communities, schools, and offices practice evacuation procedures, learning to identify alarm signals and reach designated safe areas. These drills, repeated regularly, ensure that knowledge is widespread and that residents can respond calmly under pressure. Infrastructure also reflects proactive planning. In many high-risk coastal zones, vertical evacuation structures have been built, towers capable of withstanding earthquakes and tsunamis. Signage and marked evacuation routes guide residents to safety, while urban planning integrates hazard zones into development restrictions. Cities such as Padang, Bengkulu, and Banda Aceh demonstrate how planning and preparedness can coexist with densely populated coastal regions. Scientific research directly informs these measures. Risk models identify inundation zones, structural vulnerabilities, and likely evacuation bottlenecks. Authorities use this information to improve urban planning, emergency logistics, and resource allocation. In addition, real-time monitoring data feeds into decision-making during potential events, ensuring that responses are based on verified information rather than speculation. Communication with the public is a critical component. Authorities emphasize clear, factual guidance, avoiding alarmist language while providing actionable instructions. Education campaigns, community workshops, and school programs reinforce awareness, teaching residents how to act safely in the event of seismic activity or tsunamis. Together, monitoring networks, drills, infrastructure planning, and education create a multi-layered system of readiness. While the Sunda Megathrust cannot be controlled or predicted, these measures reduce risk, improve response times, and empower communities to act effectively. Preparedness transforms the fault's immense natural power from a source of fear into knowledge that saves lives and protects property. Living with megathrust risk, the real message. The Sunda Megathrust is a force of nature that operates on a scale and timeline far beyond human perception. Its movements are slow, steady, and relentless, yet their potential consequences touch the lives of millions along Southeast Asia's coasts. Living with this fault is not about fear. It is about understanding, preparation, and coexistence with the geological processes that shape the region. History offers lessons. Past events, from the 1797 and 1833 earthquakes to the devastating 2004 Indian Ocean disaster, reveal both the immense energy stored along the fault and the resilience of affected communities. Each event has informed scientific models, monitoring systems, and disaster preparedness strategies, showing that knowledge and planning can dramatically reduce risk even in areas of high exposure. Modern technology enhances this resilience. Networks of seismometers, GPS stations, satellite monitoring, and ocean bottom sensors provide continuous insight into the fault's behavior. These systems allow authorities to issue real-time alerts, improve evacuation logistics, and update hazard maps. While scientists cannot predict the exact timing of a rupture, they can identify patterns, understand strain accumulation, and guide policy decisions to protect communities. Equally important is public awareness. Education programs, drills, and clear communication from agencies like BMKG and INATUS empower residents to act quickly and safely. Coastal communities practice evacuation routes, families learn how to respond to tsunami warnings, and schools teach students to recognize hazard signals. This knowledge transforms uncertainty into practical action. Preparedness also extends to infrastructure. Vertical evacuation towers, reinforced buildings, and urban planning that respects hazard zones reduce vulnerability. Coastal towns integrate risk assessments into local planning, ensuring that critical facilities, transportation networks, and population centers can withstand or respond effectively to seismic events. Living alongside the Sunda Megathrust is a long-term partnership with the Earth itself.